I'm Chen. Today I will be talking about Symbolic Machines and how we make reinforcement learning efficient enough for semantic parsing and program synthesis. This is work done during my PhD and also during my internship at Google. Okay, so first something about myself. I'm finishing my PhD in machine learning and AI in Northwestern. And my thesis is about how do you incorporate symbolic representations into machine learning. I have done several internships working on text similarity, semantic parsing, language grounding, and also efficient RL for program synthesis in Google Research, DeepMind, and Google Brain. And the work I'm going to present is through collaboration with Ni, Kwok, Muhammad, Jonathan, and my advisor, Ken Forbes. So as an overview, today I will be mainly talking about two of my recent work. One is Symbolic Machines, or how could you combine a neural network with a symbolic, say, Lisp interpreter to generate programs for answering questions. And another one is Memory Augmented Policy Optimization, or Mapple, of how can you incorporate a memory into, say, policy optimization to make the policy gradient training much more efficient. And the main result we have is this is the first end-to-end model trained with RL that achieves new state-of-the-art on weakly supervised semantic parsing. And this is tested on 3 of the common benchmarks: WebQuestionsSP, WikiTableQuestions, and WikiSQL. So as an overview of the task, what we are concerned with is program synthesis with generalization. So what does that mean is we are given a context, say a question or an instruction of what we want to do, and we are looking for some answer or some kind of goal, and we need to generate programs, and the programs will be executed on, say, a database or a knowledge graph, or say assistant or robot to achieve the goal or to return the answer. So there are 2 ways to train this. First is you could have some expert to annotate the true program or the ground truth. This will make training much faster because you can train from full supervision. But the problem is this requires expertise for the annotation, but it's hard, so it's hard to collect. So what we are aiming here is to train from weak supervision, or just a reward signal from whether the correct answer or the right goal is achieved or not. So as a more concrete example, one task we are looking at is question answering with knowledge base. So we have a question like, what college did Russell Wilson go to? And the answer is 2 universities. So you could maybe like train a sequence-to-sequence model to read the question and generate the answer, but it will be really challenging because it requires a lot of domain knowledge. And instead, since the knowledge is already stored in a knowledge graph like Freebase or DBpedia, it will be much more reasonable to generate a program that is used to query this database to answer the question. So the program, so if you are, I don't know if you're familiar with Freebase, it's essentially the nodes are entities and the edges are relations between them. So you can think of it as a graph. And what this program is doing is say, I want to first define the node, Russell Wilson, and then following the education edge, and then following the institution edge to find all the institutions that he attended. And then I want to find the ones with the right type, the universities that he attended. So I will talk more about the programming language we use. So another motivating example is natural language interface to database. So again, you have questions, and the answer is a number. So again, to answering these questions, we have, say, for example, this is a table from Wikipedia, or it could also be a database of some sort. So what's more interesting about this is for the knowledge base example, since the answer is an entity in the knowledge base, you could still try some information retrieval-based approach to get the answer. But here, the number is not even present in the table. You need to do some arithmetic reasoning, or basically here, just do some subtraction to get the answer. So it will be even harder for you to use, say, to avoid generating programs to answer these questions. So here the program is quite simple. You need to first find the row of Saskatoon, and then find the row of LA, and then do the subtraction and return the answer. Okay, so the framework we were proposing, we call it Symbolic Machines. So the idea is that we have neural net, for example, sequence-to-sequence model that is good at a lot of things, translation, speech recognition. And we also have the symbolic part. For example, you can have a very efficient, say, knowledge graph or a database. And you can also execute compositional queries and do, say, arithmetic or whatever library you would like to use efficiently with the data from the database. So how about we combine the two? Since the symbolic part will be hard to implement in neural network, for example, arithmetic or sorting. And the neural net can learn from, say, large amount of noisy data. Can we combine the two to learn to do complex reasoning? So from a machine learning perspective, what we are doing is formalizing the problem of program synthesis or semantic parsing as a RL problem. So essentially, you have an agent, which could be, say, a sequence-to-sequence model, and you have your environment, which would be, say, a Lisp interpreter connected to the database or the knowledge graph. Then the action will be each time the agent need to select some kind of a, say, token to output, for example. And it will observe, say, the output of the interpreter or, say, just whatever token it already outputted before, and also receive a reward whether he got the right answer or not. So the thing to note about this is, first, this is non-differentiable. So the neural part, the agent is differentiable, but the environment, since it's a symbolic computer, you can think of it as, say, an interpreter or SQL engine. And also, the reward, you get a sparse and terminal reward. So different from, say, Atari, here you will only receive a reward at the end of the episode or when you finished generating the program. And but the good thing about the environment is it's mostly deterministic, because if you output some token, that will appear. And usually, if you generate the same program, you will get the same reward or the same result. And the actions are discrete. So there are a lot of related work on this. So this is an incomplete list. Basically, there are approaches try to make end-to-end differentiable approach to augment neural net, say like Neuro Turing Machine or Neuro Programmer. And there are also approaches try to train from full supervision, from, say, execution traces or the true program or logical forms, like deepcoder or seek-to-tree. And there's also approaches try to use more maybe handcrafted rules or feature engineering in some of the components, like SAMPRE from Stanford or Stack by Scott. And there's recently some interest in, say, program synthesis with RL, for example, in this year's ACLEAR. So the main challenges we need to address is, first is, how do you model the structure in program? Because program is not just a list of tokens. And also, how do you learn efficiently from this sparse reward? Because we know that RL is pretty hard to in environments with sparse rewards, for example, like Montezuma Revenge. And also, how do you efficiently explore the large search space for even finding like the good reward? Okay, so I will go over each part of our solution to the questions. So first is a Neuro Programmer, or how do we augment a sequence-to-sequence model with key variable memory for models of compositionality? So first, looking at the question from, you can basically think this as a sequence-to-sequence problem, where you have, say, a sequence of questions, say, largest city in US, and then you would have a sequence program, say. So after, say, you can have the encoder read the largest city US, then you have a decoder generating the program token by token. So the program will be like, first we have US, then we want to find all the cities in US. So I want to hop from US to find all the cities. And then I want to do argmax using population. Basically, when you say largest city, usually you mean the city with the largest population. And but program is not just a list of tokens, because it has its compositionality in it. So in the sense of you will first write some expression, say find all the cities, and then the result of that expression will be used in a later expression, in the argmax expression. So here what we are, so basically we try to augment the decoder or with a key variable memory to model this compositionality better. I will go more into the details of how this works, but on the high level, what it does is basically say, whenever you resolved some entity in the encoder, or when you finished some expression and when you compute and get some new results, it will be pushed into a memory. And then in later expressions, you can try to pick from the memory to create, say, a compositional program. And this is like a linearized bottom-up derivation of this program tree. So let me go into more detail of how it works. So this is looking at the view of, say, a decoder. Is this how you? Never mind. So basically, when you finished one expression, say hop from US following city, then it will first be executed on the computer, say. It could be like a Lisp interpreter. And then you will get the result, which will be a list of US cities, say San Francisco or New York. And then this will be just saved in the Lisp interpreter. And at the same time, what we do is we also add a new variable into, say, the namespace, or a new, you can think of it as a new token in the vocabulary of the decoder, say R1. And also, at the same time, we will also generate a key embedding for the new variable. So essentially, the embedding is sort of like a comments of what's saved in the variable. And this is like when we're writing program, you write some expression, and then you save the result into, say, a new variable, you call it R1, and then you might write some kind of comments to say, how did I, like, R1 is saving, say, the list of US cities or something like that. So this is more like a continuous multidimensional vector comments of what's saved in R1. So that later, when you were writing, say, the second expression, the argmax, and you know you want to use some existing results for doing the argmax, then you will have a softmax over the tokens or the new variables you generated before to pick the one that suits as an argument. So in the sense that, so the key embedding is sort of like the neural part, where you let the model learn how to write the correct comments and also how to find the right variable based on the comments. And what's different from, say, memory network or neural Turing machine is, for the values of this, we will just keep it symbolic. This will be literally like a list of US cities and save this, say, in your Lisp interpreter or something. We don't try to learn continuous embedding for, say, the value at all. In this way, we avoid, say, learning an embedding for all the entities in the knowledge base. So this makes the whole approach much more efficient and scalable. Okay, so more about the symbolic computer, which is basically an interpreter with DSL and what we call code assistance. So, more about the domain-specific language. What we were using here is, say, a simplified Lisp interpreter. So in case you don't know, the program in Lisp will be just a list of expressions and with an end of program token. And then each expression will be, say, a function followed by a number of arguments. And so that will be one example of the program. And what's interesting, I think, about this is a perspective that, say, we used to do feature engineering, and now we do a lot of architecture engineering in neural net. So this is sort of doing tool engineering, or what kind of tools or functions does a neural model need to solve the task at hand, or to draw the reasoning you wanted to perform. So for example, in WikiTableQuestions, we used 22 different operations like hop, basically following or querying some property, or doing argmax, argmin, or doing a lot of, say, comparisons, and also, say, like first, last, or previous, next, something about the table structure, and also like something about the statistics. So basically from this, you can see that what type of reasoning is required with this database. And this is sort of like defining the search space for, you want the true programs to be at least in the search space. So I would say you still need some kind of prior knowledge in this. So I will talk a lot about this exacting learning part, but I want to emphasize that you will still need some prior knowledge. Okay, so another observation we have is when we write code, we would not write code on pen and paper usually, and we would instead use, say, an IDE that will pop you with, say, the valid choices for the next step so that you can avoid some simple syntactic error. And here we were basically providing the same thing for the neural network. So again, this is a view from the decoder. You have a vocabulary that contains, say, functions, predicates, and also, say, existing variables. And first, what we can do is we can use some syntactic constraints. Basically, if I know that the last token you had is, say, open parentheses, then I know I'm looking for a function at this step. So I can avoid all the predicates and the variables. And what's more interesting is we can also do semantic constraints. What this is doing is, say, the expressions so far is I want to hop from, say, R0, which is United States. So I basically want to find some property of United States. So first, I know that I'm not looking into, say, variables or functions. So I'm focusing on predicates. And what's more interesting is I can also cross off a lot of predicates because since I know you're asking something about United States, then I know you're probably looking for something like, I don't know, population or cities in, and you're not looking into, say, birthday of or parents of, because United States would not have those predicates. So this way, we can basically focusing on the properties that the United States actually have. So this helps us, say, reduce the branching factor by orders of magnitude and makes the search space much more manageable. And if you think of this, this is essentially kind of like, say, when I say a sentence like, what is, for example, what is X from? So the meaning of this depends a lot on what X really is. So if I'm talking about a person, then you know I'm asking maybe the birthplace of that person. And if I'm asking if X is a laptop or something, then you might use a very different property, maybe like the factory that made the laptop or something. So in a sense, we're using the entities to help us do disambiguation. So okay, so last part is how do we make RL efficient enough for a large search space with sparse rewards? So first, let's take a look at the, say, simplest and most commonly used policy gradient training method, reinforced. So what it essentially do is basically there's two phases. First is sort of like an actor phase where you sample a bunch of programs, say, from your current model, a bunch of samples from your current model, and you will collect, say, the reward for the samples. And then there's a learner phase where you send all the samples to the learner to compute a gradient and update the model, and then the actor will use updated model to generate more samples. So basically, you have a loop like this. And if we take a closer look at how it works in our case, it will be like, so each environment is sort of like you have a question, like, and also like a table. I'm omitting the table here. Basically, you ask which nation won the most silver medal. And then the actor is facing a large search space. Basically, if you have, say, the program length, if it's, say, 3 or 4, you have like at least tens of millions of possible programs. And so each program will be, say, some number of expressions, and each one will have some probability and also some reward. So, and you cannot enumerate the whole program space, so you would need to do sampling. And so here I'm using a more visually friendly way to represent the programs, and also using the sign for to represent the reward. So basically, one problem is the reward is very sparse. So in the, say, tens of millions of programs, there's maybe only 5 programs that can get you the right answer. So if you just, at the beginning, we just have like a randomly initialized model. And if you just randomly generate programs, it will be very hard to see any good one. So the reward is sparse. And what's more problematic is even if you sampled, say, in one iteration, the model got lucky and you sampled one good program, it is only used for training the model at that one step and then discard it, because reinforce is on policy training. Each time you sample a bunch, you train, and then you discard that, and then you sample another bunch of samples. So the good ones rarely happens, but when it happens, it's used only once and then forgotten, so which is really bad. So one one straightforward way we had to fix this is what we call augmented reinforce. Basically, we try to augment it with a memory. So this is our first attempt when we work on the problem in 2016. So the idea is what if we have a buffer and we just save all the good programs for the questions. Say if I know program A generated like a good reward, then I just save it in the buffer. And then when I train, I use sort of like a linear combination of two training objectives. So first is I still have the expected return objective, but I augment it with, say, a maximum likelihood objective that, say, try to maximize the likelihood of the good one saved in the buffer. So this helps the training to accelerate a lot. But the problem is, first, this is sort of like ad hoc, like just combining two training objectives. And the gradient is sort of biased. It's not the true policy gradient. And another problem is this is not robust against spurious programs. So what is spurious programs? So the spurious programs, it basically means the programs that get the right answer, but for a wrong reason. So for example, this is a table of, say, maybe some Olympic game or some sort with, say, gold and silver, bronze medals. And the question is which nation won the most silver medal? And the correct program should, say, do argmax using the silver and then find the nation name. But there's also a lot of other programs, say, they are doing argmax using the gold medal or, say, the bronze medal, or doing argmin with the rank. They can also get the right answer, but apparently for the wrong reason. So if we just use this simple way of, say, maximizing the likelihood of, say, the top K programs, what you're doing is you're not only maximizing the likelihood of the true program, but also maximizing likelihood of all the spurious program. So this basically introduces a lot of bias into your gradient. So as a more principled approach, so this year we propose Mapple, or Memory Augmented Policy Optimization. So essentially the main idea is still the same. You still want to have a memory buffer of, say, good programs and their reward. But observation we had is you can actually just decompose the expected return objective into two parts. One is as expected return within the memory buffer, and then expected return outside the memory buffer. And then if you wait, you can think of it as this. So if you're doing sampling on both sides, this is basically stratified sampling. I divided the whole population of programs into two parts, and then I sample from both sides. And as long as I weight, so each side by the probability mass of that side, then this addition or this summation is still giving me the unbiased gradient. So, but what usually happens in our case is the ones in the memory buffer will be small. So actually we didn't put a lot of constraints on what you can put in the memory buffer. So here we are using, say, the reward to pick the programs with the highest reward to put in the memory buffer. You could also say, if you have, say, demonstration or fully supervised data, you can also put them into the memory buffer. So essentially, since usually the memory buffer is small, we can actually enumerate all of the probes. Say there's usually, for example, like 10 programs in the buffer. We can enumerate all of them in the buffer. And then outside the buffer, we can still do sampling. And this gives us unbiased estimation and also reduce the variance, because within the buffer, we can enumerate all of them. So another good thing this gives us is more robust against, so first is more principled, it's a true gradient, and also it's robust against spurious programs. So can I write something here? Yeah. So the reason why is, so the first approach will be, for example, if I use, say, to represent all the programs. So essentially, I'm computing like a sum of all the gradients with respect to the log likelihood of all the programs in the, say, memory buffer. And if we are using the policy optimization approach, or basically comparing, say, log likelihood training with policy gradient training, the difference will be this term. Essentially, the policy gradient is weighted by the model probability of the program. So it's sort of like if the model already like this program, it will give more weight in terms of gradient. But for log likelihood, it's basically maximizing everything together. So what you will see is, I should use this. So if I just do like log likelihood training, is maximizing the likelihood of everything with an equal weight. But if I'm doing, say, more like policy gradient training, what it has is if the model, so there are hard examples like this, but there are also simple examples like maybe like only silver medal is, there's only like one true program for this. It will be less ambiguous. So the model, if it prefers, say, the true program a little bit, then the policy gradient training objective gives it a way to escape from, say, the spurious programs. So what we see is usually if we do policy gradient training, then the correct program, if it at beginning it has slightly more, say, probability, then it will accumulate. And then at the end, say almost, say, maybe like 99% of the probability mass is on the correct program. And then all of the spurious ones will be ignored. Essentially, you gave the model, so it might not always happen, but you give the model a choice to, say, ignore the spurious programs because of this term. Okay. So again, like looking at a more visually easy way, we were essentially dividing this into two parts. You have the good ones in the memory, you can enumerate, and you weight that by P of the memory buffer. And then you also have the samples from outside the buffer, and you weight that by 1 minus PB. So there's still, say, two problems. So one of the problem is, say, PB can be very small because you weight them by PB. And this, if you think of, if you think of the policy gradient objective, is sort of unavoidable if you follow the true policy gradient. So what we are doing essentially is, can we trade off some bias in the initial stage for faster training? So what we are doing is essentially clipping the probability or the weight of the memory buffer to be, say, if it falls under, say, 0.1, then we fix it at 0.1. So at the early stage of the training, we enforce it to like always pay certain attention to the good programs in the memory buffer, even though it doesn't want to. But as long as, say, PB grows more than alpha or more than, say, 0.1, then the clippings will not be active anymore. Then it will essentially be just policy gradient objective. So that we can usually see that the percentage of clipping will drop as training goes on. And then towards the end, none of the clipping are active anymore. So we are sure that at least the local minima we found is also the local minima in the true policy gradient objective. But at the beginning, we want to introduce some bias for faster training. So another problem is we still need, so we have a way to, say, make the weight to be not so small, but we still need to first find, yes?
Do you initialize your memory buffer in some way, or do you just start training from scratch?
So in the examples, we initialize it from some random sampling at the beginning. So we not randomly sampling, but more like systematic exploration, the thing I'm going to talk later. But basically, we want to initialize it with something. So what we are doing is systematic exploration, essentially. The problem we are trying to address is if, say, reinforce only use sampling for like finding the good programs. But the problem is, if you look at them after the model is trained for a while, a lot of the samples will be repeated if you just do sampling from it. And if you look at between two iterations, there will be even more repeated samples because each step the learning rate won't be too large, so the model would not change too much. So it will still like have a lot of repeated samples. So instead, what we are proposing is, can we do a more systematic approach for exploration, or can we avoid wasting computation, maybe based on by trading off some memory? So here the idea is pretty simple. Basically, we try to keep a hash table, or say a Bloom filter, to save the already explored programs, so that when we want to explore more, we will enforce the exploration to generate some truly novel programs, some programs that is not in the hash table already. So in this way, we trade off, say, memories, like a few, maybe a gigabyte of memories, but the speed is much faster because we don't generate any repeated samples when we generate samples for exploration. So what this looks like is essentially, so this is a simplified visualization of the search tree. So first you generate some programs, and then I know that those two nodes, or say all the subtree under those two nodes are already fully explored. So I know I don't need to go into those two nodes anymore. So next time the model is enforced to pick some other approach, and then you will gradually, say, cross off more and more nodes as you do like a systematic search over the tree. So we keep this systematic exploration running while the training, and we also run this with a random model for some time before the training to collect some good programs. So putting all the things together, essentially, we still have the actor and the learner phase, but what we are adding is a memory. So when you are getting training samples, using samples inside the memory and also samples outside the memory. And we were adding the marginal likelihood constraints, basically the clipping to make sure the memory always gets some attention, and also the systematic exploration for efficiently finding some good program. Yes?
So when you switch to systematic exploration, wouldn't it bias your probability of the buffer?
Yeah. I think it's good here. So basically, we have, so there's, I think, two answers for that. One is, say, when we're drawing the, say, exploration samples, is different from, say, the training samples. So we have, say, exploration sample, which is sort of biased because you enforce it to generate something new for collecting good programs to put into the memory. At the same time, we also draw, say, unbiased sample from your model. So for the training sample, it's different from the systematic sample. And also, if we pick, if we put things into the memory, so we were sort of leveraging the advantage that the environment is sort of deterministic. So for the things we saved in the buffer, which could be, say, from systematic exploration or from demonstration or whatever way, but when we were computing the gradient, we will use the current model to compute the gradient, or to compute, say, the probability of all of this, to compute PB and also computing the gradient of that. So essentially, that's why we still have, say, an unbiased gradient, although the samples are collected from, say, some other different policies, which could be biased or from, say, human demonstration or something. But because this is mostly a deterministic environment, we don't need to worry about, say, the environment stochasticity. We can use the current model to like recompute all the gradients or all the probability. Okay. So this is an overview of the approach. So, but another big problem for like applying RL or a practical issue is how do you scale up? Because for RL, you essentially are doing like solving the problems through trial and error. You need to efficiently generate a lot of programs, essentially. So here we were taking a more like actor-learner architecture for dealing with this. Essentially, we first do sharding over all the training set, basically split them into multiple shards. And then we have multiple actors. So each of them could be run on a CPU, because the neural model we use is usually small, but the bottleneck is more about, say, generating a lot of programs and then evaluate all the programs. So each actor is interacting with a bunch of environments for generating the programs or samples, and then that will be pushed into, say, a sample queue. And then you have a learner, which could be using GPU, because it's doing more like computational intensive work by, say, each time it fetch a batch of programs from the queue and then do backpropagation and then update the model. And then periodically, the actor will update their model or sync their model with the learner. So we have been using this before, and I think DeepMind has a more clear way to formalize this kind of actor-learner training. So essentially, this gives us almost orders magnitude scale up with. So this is done. The experiments we're doing is on AWS using, I think, G3 X large, which has a 33 CPUs and 2 GPU. And the code is open sourced, which can be used to replicate the result. And essentially what we saw is with the actor-learner architecture, we can basically address the bottleneck in generating programs and have orders magnitude speed up. Now the experiments can be finished in just a few hours. Okay, so about the experiments, we essentially evaluate the approach on 3 most of the common benchmarks. First is WebQuestionsSP that contains around 6,000 questions collected from Google Suggest and then cleaned up by Scott E. And so the thing about this is, first is the open domain. It contains grammatical error, and also the answer could be multiple entities. And the main challenge of this is more about, can you find the right property among, say, the large schema or 23,000 properties. And there are a lot of different approaches applied on, say, QA with Freebase. And what we have, the main result is this is the first neural network or end-to-end neural network approach to achieve state-of-the-art on semantic parsing with weak supervision and a large real-world knowledge base. And the previous best approach is by Scott, and our approach is significantly better on all of the metrics. And so we did an ablation study with augmented reinforce. Essentially, what we see is iterative ML is sort of like, what if I only do maximum likelihood training with, say, the top K buffer? So the training will be much faster, but basically you will have a suboptimal result. So if I only use reinforce, what we see is the training will sort of get stuck. And when we look at the samples, essentially reinforce can only get the programs that is 1 expressions long, because those are the ones it will be easier for it to explore and also learn. But it's hard for reinforce to get over 1 expression. And augmented reinforce get us the best result. But I have more systematic comparison later. So also we did a lot of approaches to reduce overfitting, because this is a relatively small data set. So things like dropout, pre-trained embedding, and also anonymize the entity tokens. For example, who is the wife of Obama? And then we will anonymize Obama to be some special token. This makes each question is more like a template. So it's stuck a little bit. Okay. So the second data set we look at is WikiTableQuestions. So in the Freebase or the web questions data set, the questions are not super compositional. The challenge is more about finding the right relation. But here the questions are basically designed to be compositional, but sometimes a bit unnatural. So if you look at some of the questions, some of them seems a bit twisted, and some of them doesn't really make sense without the table. So like, in which city is the first time with at least 20 nations? So they try to create some compositional data sets using Mechanical Turk. And also, at test time, you are given new tables. So the model also need to generalize to new tables based on the column name. And also, there's more operations, and because the questions are more compositional, you usually need a much longer program. So usually, like at least 2 or 3 expressions, sometimes 4, to answer the questions. And the main result, so there's many different approaches applied on this, like feature engineering with log linear model, some neural net approach, and some combination of both, say like log linear model first, and then with a neural re-ranking. And our model, the single model, already matched so the most recent state of the art on this result, and without using any of the feature engineering. So the top one is still using log linear model with some handcrafted rules and feature engineering. So our model can basically be single model can be comparable to that without the manual engineering, and a simple ensemble can give us significantly better result. So there's also some other approaches that uses dataset with more human annotation. For example, I think Jiang, while he was in AI2, did some work on that. So we also run the same model. We have been developing for WikiTable, but then this new dataset come along, but it's annotated with the true SQL, basically the ground truth programs. So we applied our model, and we see that our model is essentially on par with a lot of the state-of-the-art results at that time. And if we do a simple ensemble, we can even get better. And all of the previous approaches are even like, there are some new approaches coming out, I think, getting better results, but still most of them are using strong supervision. And we are training only from the questions and answers without knowing the ground truth. So what's more interesting from a machine learning perspective is we did some ablation study on the training objective. So on both of this, essentially, if we just do reinforce, none of them can get like any reasonable result at all, because the programs are usually longer, so it's hard for reinforce to even sample any good ones. And our results achieve the best, and we also tried a bunch of other objectives, like doing log likelihood over the buffer, or doing, say, marginal log likelihood over the buffer, or like more like an EM approach, using the good examples we see. And none of them can beat Mapple. And also the two techniques, like systematic exploration or the clipping, are also crucial to get the result. So when looking at the learning curve, we found some more interesting trends. So the blue one is Mapple, is our main approach. And the red one or the green one are the marginal likelihood-based approach. And the yellow one is a likelihood approach. So first, the yellow one is not good because it's not robust to, say, spurious programs. So MML, or marginal likelihood-based approach, are more robust to spurious programs, and it's also training much faster. So this is a log scale, and you can see that at the beginning, at the earlier say steps, the log likelihood-based approach are usually better than the reinforced-based approach, and it will reach the optimum, say, like almost twice as fast, almost twice faster than, say, the RL-based approach. So for MML, it probably reaches the maximum at around 5,000 steps. But what's good about RL is, although at the early step, the training is slower, but it will keep going for longer time, and say around maybe like 10,000, between 10,000 to 15,000, it will achieve, say, the best result. And the best result will be like better than the likelihood-based approach. So I guess for RL, you need more patience for waiting the learning to finish. Okay, so there are some examples to basically give you a better feeling of what kind of programs we generate. So there are things about, say, constraints, like what college did Russell Wilson go to, the example I showed earlier, where you need to do, say, 2 hop from the Russell Wilson, and you also need to filter using the type of the entities. So on WikiTableQuestions, there are more interesting semantics, like sometimes you need to use, say, superlative, like who scored the most points. You need to use argmax and then find the property, find the name. And there are things about difference, where you need to find the 2 rows and then compute the difference of some property. There are things of exclusion, like within something, like which other person was born in Tusa. So you need to find the things that has, say, Tusa, and also find the things that doesn't have the name of within, say, Prince. And there are things of comparison and count, like in how many games did Sri Lanka score at least 2 goals, you need to use, say, greater or equal, and then count the number of rows. And there are things about the structure of the table, like which nation is before Peru, or which nation is after, say, X, where you need to find the row, and you also need to use, say, previous or next to, like, using the structure of the table to answer the questions. Okay, so in this talk, I talked about 2 of my recent work. One is Symbolic Machines, or how can you combine a Neuro Programmer, or say a neural sequence-to-sequence model with a symbolic computer, say a Lisp interpreter, to generate programs for answering questions or maybe achieve some goal. And also, so that one is published in ACL last year. And a more recent work, Memory Augmented Policy Optimization, or Mapple, of how can you augment the policy gradient training with a memory to make the training much more efficient. So this one is submitted to NIPS. We got some good review, so hopefully we'll get in. And thanks. So all of these 2 papers you can find on arXiv, and the code is also open sourced for replicating the result. Yeah. Any question? Yeah.
During training, how much of your policy probability is allocated to the memory, the execution traces in the memory buffer over time? Because essentially, how does what does that dynamic?
Yeah. So if you think of this, so basically, for example, if we are dealing with, say, a binary reward, right? So we are saving all of the good ones in the memory buffer, right? And also, say, the bad ones outside, we will need to sample them, right? And you can think of it as basically the probability on the memory buffer is sort of almost, say, approximately equal to the current performance of the model. Essentially, if your model pays a lot of attention, pays a lot of probability on the memory buffer, that means it has higher probability for generating the right programs, right? Let's assume you collected all the good programs in the buffer. So the growing with this is, so what I'm saying is the probability it put on the buffer sort of like grows as a training. So similar to the learning curve, because the more probability it puts on the memory buffer means the more likely it can get the right answer. Yeah. And for RL training, usually you see a curve as at the beginning it's like plateauing for a while, and then once you get it, it will have like a faster training phase, and then maybe it will plateau again for a while for like collecting some examples. More questions? Yeah.
So at that point, did I get it correct that you're using the bottom equation?
Yeah, so it's more like the bottom equation.
So if a spurious program in the beginning ends up getting a high probability, it will keep growing up higher and higher, and the correct one has no chance of coming back. Does that happen?
Yeah, I think that can still happen. That's why I say the model is given a chance to escape from spurious programs. But whether it can or cannot depends on the task. Say, if your task is very, say, adversarial, like there are a lot of very short spurious programs. And actually in WikiTable, it has something like that, because, say, there are some bias when the Turker creating the question, because you ask the Turker to create some question based on the table, then usually they will look at the top or the bottom of the table and then just think of how do I create some question that make that as an answer. So a lot of the question can be, I just take the top of the table or just take bottom of the table. That is just like one expression, and that will be like spurious. So that kind of that's still like a big problem for this data set, I think. But that's why people are, say, one is collecting more annotations. So if you think at each question is more like a unit test for the program you're looking for. And if you only have one unit test, then you probably will not like find exactly the program you're looking for. So if you have like 5 unit tests, then it will be much easier to make sure the program is not spurious. Or hopefully we can find some better way of, so what we find helpful in our case in practical term is if we can, say, before training, use, say, a random policy to already accumulate a number of programs, that really helps because you already have some diversity in the memory buffer. But I think this still is a big problem when training from weak supervision, like how do you avoid the very hard, spurious programs? Yeah.
So a more futuristic questions. So multiple choice questions like math SATs or science we have in Aristo fit very well here in the sense that there's natural weak supervision in the answers, but they're substantially harder than the data sets the community has worked on. So I'm curious, if you look ahead, 1, 2, 5 years, what do you see as the challenges that you think we can solve in the next year or two to extend the techniques? And what do you see as much harder?
Yeah. I haven't directly worked on the science test before, but based on my experience looking at those, I think first they require a lot of word knowledge. So I think that we either hope like some gigantic neural network can get that from the unsupervised training, or maybe we need to extract that. For example, the knowledge about like physical process or something, you might need to extract that from, say, textbook or somewhere. And then, so comparing to this is we usually have, say, like a fixed like knowledge base, and then you try to basically answer questions based on the whatever knowledge is in there. So in this case, I'm thinking we probably need the knowledge base also need to grow based on the text, whatever text you have, or based on maybe what kind of domain you're looking for. And it also need to be more, it also need to contain much more than just triplets or facts. It need to contain maybe knowledge about processes and also some arithmetic reasoning. So basically contain much more things that can also help the reasoning. So then we can still maybe do more like weakly supervised semantic parsing, where if you can extract the correct fact, then combined with, say, it could be like rules or some knowledge about the process that together can solve the question. But I think, again, like we still need to advance the things on semantic parsing, but we also need to advance the things in terms of semantic parsing of understanding the text. So here, the semantic parsing is about how do you understand the questions, but we also need to think how do you understand, say, the textbook of extracting those knowledge. And then together of this, maybe we have some chance for like advancing this metric on science test.
So that's a great answer, but let's assume for the sake of argument, as you said, that we have the requisite knowledge both of processes and background knowledge in some neural network.
Yeah.
Then do we need to extend semantic parsing, or do you think the current techniques will then be able to solve the problem?
I think it depends on how much. So basically, when I look at semantic parsing, I think essentially we're solving two problems like altogether. One is about understanding, one is about reasoning. So like when I ask, so there are things about like very easy to understand but hard to do, maybe like how do you prove this math theorem or something. It's very easy to understand what you want me to do, but it's very hard to do it. And there are also things like the question is ambiguous, like the reasoning is easier, but the understanding is hard. So I think for the things that the understanding of the question is the main challenge. I think we already made a lot of advance, but the problem will be more like if it requires a lot of reasoning, how could you, I think RL could still be helpful in terms of those questions, but basically, the more domain knowledge or like word knowledge you have, and the better chance you will have to solve those questions, because those are not just about understanding the question, but more about like how do you actually prove the theorem. Yeah.
So that's actually a very optimistic answer for these data sets, because I think they fall in the other category, right? The questions can be difficult for the machine to understand. Once you understand the question, since it's for, say, an 8th grader, we're not asking to solve Fermat's last theorem.
Oh,
right, it's usually just a few reasoning steps.
Yeah, yeah. So maybe also I guess like the size of training data is also important, because usually like it's hard to collect in large amount of the tests. I mean, or either we try to do some kind of unsupervised training with a textbook, like try to ask yourself some questions, how to answer them, or some more creative way to get more data. Because I think in general for semantic parsing, the size of the data set is a problem because it's hard to collect a large amount of data with, say, database or knowledge graph. Yeah.
So we'll stop. Thank you very much.
Cool. Thank you.